Hello, everyone. Welcome to our Bay Area Rust meetup. Today we have a good set of speakers talking about GPU glyph rasterization, Rocket, and the Orphan rules. As always, thanks Mozilla for hosting this event, or giving us space to host this event. Before we start, on March 25th, there's a worldwide Rust Bridgeathon where we'll be teaching Rust. If you'd like to help out, we're hosting one here.
And building tutorials.
Oh yes, and also building tutorials. If you want to help out, we'll be hosting one here at this space on March 25th, and there will be other versions of this all over the world. So do come, help out. And if you have friends who want to learn Rust, send them as well. We have extended the underhanded Rust deadline so that people can get more time to submit. We also have we also have an example up, the Quad Bank example, which contains some sample code which you are free to lift and use for your stuff. There's also a list of resources on how to make your code more secure and prevent underhandedness in your code. The deadline is now March 31st. So go forth and write bad code. Yes, we love writing bad code. Yeah. Our lineup is Patrick talking about Pathfinder, which is a GPU-based font rasterizer. Sergio, the maintainer of Rocket, talking about Rocket. And Boats, talking about boats. No, talking about Coherence and the Orphan rules. And maybe Boats. All right, so I'll hand it over to Patrick. There you go. Great.
All right. Hopefully this will work. Good, it worked. There. Hi, I'm Patrick, and I'm going to talk about fonts. Hope everyone likes fonts, because you're going to be hearing a lot about fonts. For those who don't know, I've been working on Rust for a lot longer than anyone should be working on Rust. And I've been working with Rust on Servo and lots of graphic stuff. You may have remembered my web render talk that I gave last year. This is kind of, a sequel, follow-on to that work, where we, with web render, we were taking the GPU and accelerating web content in Servo. And with this, we're accelerating more stuff. So we're accelerating the way we render fonts and text. So I'm going to be talking about several things here. I'm going to talk about why we care about this, the literature that's appeared in the past on how to render text, how it works, the nitty-gritty details, and I'll give results in a demo. And hopefully the demo will show up well for you. It's kind of hard to demo GPU stuff on AV, but I'll do the best I can. So why do we care about font rendering in the first place? Well, the most obvious reason here is performance. Why do we care about making font rendering better? What's wrong with the existing font renderers? Well, the problem is that they can be slow because they don't take advantage of the hardware that's in modern CPUs and GPUs. So right now, the font rasterizers that exist, font rasterization is a very old problem. People have been working on it since the 80s, if not before. We use very old code bases to rasterize our CPUs. We use FreeType. We use the Windows font stuff. All that is about probably 20 plus years old. And it's been working great, but much as in the web rendering space, there's been new advancements since then. So we would like to take advantage of new hardware to be able to rasterize fonts. And in particular, people are like, well, what's the use case? Why do I care about making fonts fast? And one of the most obvious things here is when zooming a page, right now it becomes blurry. And if you haven't noticed this, try open up your iPad or whatever, and zoom in, don't release your fingers, you'll notice that it's blurry. The reason is that you can't rasterize fonts fast enough, or at least in many cases you can't rasterize fonts fast enough. So you end up with blurry text, and because they're just using a very simple GPU upscaling filter, and they're not actually re-rasterizing the font from scratch. So that's kind of not the greatest user experience. We would like to have more fluid apps, and to do that, we need to actually, in some cases, accelerate text, because in many cases, text is actually the limiting factor. In WebRender, for example, on frames where we have to render text and it's not cached, oftentimes rendering the text on the page costs more than rendering the whole rest of the page. So we would like to make fonts faster. But vector graphics aren't just useful for fonts. There's all sorts of APIs on the web that use vector graphics. PDFs, I'm sure everyone has dealt with a slow PDF that takes forever to zoom, forever to scroll. There's Canvas on the web that gets used a lot. SVG is also used quite a bit. There are new specs coming down the pipe that use vector graphics even more. It's like CSS to custom paint, part of the Houdini spec. So vector graphics are important. And we start with fonts, but Pathfinder's a generic vector graphics rasterizer. It can rasterize a lot of things. So this is very much a work in progress. We're going to see how far we can push it. So whenever I talk about GPU path rendering, everyone asks me, what about these other things? There's been a lot of work in GPU path rendering over the past years and decades, because a lot of different people have wanted to solve this problem in a lot of different ways. So unfortunately, I could spend more than one talk talking about all the different possibilities here. So if you know about one and I don't get to it, I apologize. We can talk after, you can ask them questions, but I'm going to get to the most popular ones here and explain why Pathfinder is different. So one of the popular ones here is something called signed distance fields. Has anyone heard of them? People? Okay, a few people. So this is in the seminal paper on this is something called Improved Alpha-Tested Magnification for Vector Textures and Special Effects. So it's SIGGRAPH from Valve, has a lot of screenshots of Team Fortress 2 in it. It's pretty cool. They used it for vectors, basically scaling up textures, text that appeared on walls and stuff. So you see this in games. It started in the games industry. This is the actual picture they show in their paper, where they have their little Lambda logo, and if you use the native GPU blending, the regular stuff like this, like I talked about with the blurry pages, you get the thing on the left. You can do a little better with a well-known trick, the alpha testing in the middle, but it still doesn't look very good. It becomes all wiggly, and they improved it to be the one on the right, which looks better. It's not perfect, but it looks better. So signed distance fields are basically a specific way of encoding a texture. They look like this if you visualize it and dump it from the GPU. So they're kind of glowing. They kind of look like glowing text. This is an app called Mapbox. They had a very nice blog on this thing. They use it for drawing their text on the GPU. So they put a whole bunch of fonts in one big texture, and they can rasterize with that. So how do SDFs work? Well, SDFs, the thing is, they aren't actually vector rasterizers. They are just more of a way to scale up textures and have them not look really bad and really blurry. So they don't actually draw the curves that are inside fonts. They instead just blow up some already drawn fonts, and it looks nicer. So that's kind of an issue, because where do you actually get that signed distance field in the first place? Well, you're basically actually drawing the font. So this can be a problem when you're in a web page scenario. We just downloaded a font, and you might say, oh, well, you signed distance field to render on the GPU. Well, the problem is, in order to get that SDF, you have to actually render it first on the CPU, and that is often many times slower than actually rendering the font on the CPU to begin with. Usually what they do is they render it on CPU first at high res. They compress it. That's not a problem for games, because games actually, they can just render it and ship the rendered result as part of the game, but that doesn't actually work on in normal circumstances. There is an alternative. There's a project called Glyphy, where the curves can be, you can convert the curves to arcs and then do some cool math to actually render them directly, but converting the curves to arcs is very expensive. In many cases, you might as well have rendered the glyph already. So that's an issue. So pros, with fine distance fields, popular. The shader's really trivial. You can get okay anti-aliasing. It's not great, but it's better than having it look really jagged. And the really nice thing is why this is popular in games is that it works on every GPU, even ancient ones that don't have any shaders at all. You can still configure GPUs that you can render them. So that's pretty nice in that use case. The problems, though, you have to make the SDF in the first place, which basically kind of eliminates the point in a lot of cases. The anti-aliasing isn't good, and because it's not actually rendering the curves, when you scale it up past a certain amount, you get these rounding artifacts. And here's an example of what happens when you scale up an SDF too much. It looks like curves, but it sure doesn't look like how it's supposed to look like. So that's an issue. So here's another approach. This is a very popular one, Loop Blinn, named for the authors at Microsoft Research. You see this a lot when you see people talk about vector graphics on GPU. A lot of times this is the core of their algorithm. NV path rendering, for example, is NVIDIA's extension for path rendering. It's just it's a very fancy variant of Loop Blinn. So a lot of times when you see people talk about GPU vector graphics rendering, they're really talking about something built on Loop Blinn. And here's a really nice image I found from Evan Wallace. This basically shows visually how Loop Blinn works. You trace out, you draw a whole bunch of triangles. That's what GPUs draw. And you set it up so that you flip. So that you flip what's called the stencil buffer every time you render a pixel, and that gives you a sort of outline. That gives you a sort of hull that encompasses the glyph, and then you cut out in the shader the parts in order to make your curve. So the first part of this shows actually drawing the outline and getting the fill right using the stencils, and then the second part shows running the shader and cutting out the parts. And just for some more detail, you render the quadratic Béziers as triangles. Cubics are more complicated. Cubics are usually what you see in vector graphics and more complex fonts nowadays. You assign varyings, and the math works out so that all you have to do is check if you do a square, subtract, and check the sign. And it works out because of quadratic equation math. What's great about this is that it's simple. You don't need CPU side setup if you have quadratic Béziers because you just literally draw all the triangles. You draw the control points as though they were triangles. And this works in any GPU with a shader. It doesn't matter how bad the GPU is. The shader is literally squaring a number, subtracting, and checking the sign. Any GPU can do that. So that's why, especially since this came out, many years ago, this was very popular at the time. The problem with Loop Blinn is that when you use the stencil for the fill rule, so you can see back here, it's drawing a whole lot of pixels in order to actually figure out what the final ones are. You can see all those intermediate pixels that got drawn. And effectively, mathematically what it's doing is recalculating the winding number, which is used to determine whether a pixel is in or out, for every pixel entirely from scratch. This isn't how most CPU rasterizers work. They actually do an entire line at a time. So this is doing a whole lot of work that wouldn't be needed in a CPU rasterizer, or a more efficient rasterizer in general. The anti-aliasing isn't as good. It can ironically anti-alias curves, but it can't anti-alias lines without using the hardware. And that's a problem because the hardware anti-aliasing is lower quality than rasterizers that do exact trapezoidal calculations. So basically, in effect, the hardware GPU can give you maybe 8 shades of gray or 16 shades of gray, but modern CPU rasterizers will give you 256 shades of gray. So there's a big difference, and you can actually really see it. The other thing is that the math doesn't work out quite so nice for cubic Béziers, which are becoming common. They had to end up having to do a whole bunch. it's not a complicated, but it is some CPU side work. It's not quite as clean and nice for cubic Beziers. So here are some others that I don't have time to talk about, but there's a vector texture approach. There's actually a very interesting one that came out last year where it's actually kind of similar to Pathfinder, but it uses a sparse representation, which requires sorting on GPU. There are many others. If people want to talk about them more, I'm available. But I'm sure people want me to get into actually how Pathfinder works. So Pathfinder is this new approach that has basically 3 steps. First of all, on the CPU, we upload the control points to the GPU. This is just like loop-lin. And the second one is on GPU. We split up the curves, and we compute delta coverage. There's something called delta coverage, which I'll explain in a minute. And finally, we have a separate fill step. So whereas some algorithms have 1 step, this actually has 2. But that gives us a lot of advantages, as will become clear in a minute. So the first part is pretty boring. Parse the true type outlines. Well, I say it's boring, but it actually has a lot of details because true type is a really complicated format. There are 4 different ways to store outlines in open type, and it's a mess. But once all that is done, once all that relatively uninteresting work is done, we have a whole bunch of control points, and they're uploaded to the GPU. So our first step is to tessellate. So we have a bunch of control points, but GPUs don't know how to render control points. They know how to render triangles. So what we do is we divide the curves into small lines. And right now it's 3 pixels. We could change that. It's just arbitrarily decided that 3 pixels is how much we want. We actually expand. We draw the pixels as far as the GPU is concerned, as the lines are drawn as little rectangles, causing an annoying complication when they overlap. This is done using special hardware that's been in GPUs for the past, maybe 7 or 8 years, or 5 years, is called the tessellator. This is tessellation shaders in OpenGL, or Holland domain shaders in Direct 2D, or Direct 3D rather. And so we can actually do all of this on the GPU. It'd be possible to do it on the CPU. I've tried it on the CPU. It's pretty fast, but why do that when we can do it on the GPU? So notice that this is not doing what a lot of other rasterization algorithms do, in that they turn the whole shape into a bunch of triangles. We're not doing that. We're only turning the curves into lines. So we're only rasterizing around the edges. And that makes it a whole lot simpler than converting the whole thing into triangles. So next we compute delta coverage. This is broadly the same algorithm that Rafe used in FontRS. So his blog post is very good. So I encourage you to go read it. But briefly here also, the Pathfinder calculates the area of the trapezoid, and I'll have a diagram in a second, and stores the difference between the area and the area of the pixel above it. So you treat every line as, or you consider the shape formed by every line and a trapezoid extending from the line below to the pixel. You treat the pixel as a little square, and you compute the exact area of the trapezoid covering that square. And here is, there end up being a few special cases. So the colored areas are the area that we're computing, and the dashed lines are the actual pixels. So we treat the pixels as little squares, and you calculate how the area of the shape covering each square. Since we've already divided the curves up into lines in the previous step, we only have to deal with lines. So we only have to deal with triangles and trapezoids. So remember that we're actually storing not the area, but the difference between the area and the area of the previous one. That's why there are a few more cases for the bottom, because the area isn't one. It's the area that we store for those bottom pixels isn't 1, but it's 1 minus the area of the one above it. So the shader ends up having a few special cases when for the cases where the line is 1 pixel, or the line touches 1 pixel, the line touches 2 pixels, and when the line touches 3 or more. The 4 pixels one should actually end after the 7. But does this make sense? Does anyone have any questions about this? I know this slide is confusing. I tried to make it as not as confusing as I could. Okay. So the result is something that looks like this. It's actually a floating point frame buffer. So what gray is 0, white is 1, black is -1. You end up with something that looks like this. So you can see the white areas are, if you imagine a ray going down, the white areas are where you start drawing, and the black areas are where you stop drawing. So you can see, for example, this W over here, you have the white area because you're starting drawing at the top, and the black area because you're stopping drawing at the end. So that's what you end up with here. And the really nice thing about this is that to build this, we only had to fill around the edges. We only had to draw around the edges. We didn't have to draw anything in the middle. You notice that the inside every glyph is the same color, the gray, as outside. So we don't actually have to draw anything there. So this cuts down the amount of work that we have to do a lot. But of course, this is not what we want to draw. We actually want to draw the fonts. So we have the final step is actually accumulation, where we just march down every column in parallel and just do a prefix sum. So if you see that, if you see this, as you start, the white areas are +1. So we start filling, and until we get to a black area, which is -1, then we stop filling until we go down, and we essentially sweep from top down. So all columns in parallel. If you actually notice there, it's a little more complicated than that because we take advantage of the fact that there are gaps here and actually sweep down all of these at the same time. So we end up with quite a bit of parallelism. We render lots and lots of glyphs all at the same time. So we don't have to issue a separate draw per glyph. We put them all together into one atlas, so we can fill many, many glyphs all at the same time. The issue with that, this is where the details get kind of annoying. We have to use a compute shader for this. We have to use GPU compute. We can't use the regular GPU functionality, at least in one pass, because GPUs normally want to shade every single pixel at once. They want to draw every pixel at once, but we can't do that because we can't draw a pixel until we draw the pixel above it. So this is what compute shaders are for. OpenGL 4.2 has them. They have a feature called image load store, which is really cool. It basically gives you get pixel and put pixel instructions inside your shader, so you can do whatever kind of drawing you want. And so we take advantage of that. Unfortunately, that's not available on Mac in OpenGL because Apple doesn't implement OpenGL features newer than half of 4.2, which doesn't include. Not including the image load store, so we use OpenCL instead. It's an alternative. You can interoperate between the two. So now on to the implementation. So right now, Pathfinder you can find it on GitHub, and it supports TrueType and OpenType font outlines, a whole bunch of containers. TrueType is awesome because you can put it in like 5 different containers, and you have to be able to parse all of them. We have subpixel glyph positioning. It's a little buggy, but it's in there. We have simple shaping. Don't use this. Don't ship anything with this, but it'll let you put "Hello World" on the screen. But don't try any other language. And also experimental subpixel anti-aliasing. Subpixel anti-aliasing, for those who don't know, lets you use the fact that LCD screens have little colors that say. Or the dots on the LCD screens are red, green, blue, red, green, blue, red, green, blue in that order, so you can actually turn on only some of them and not others to kind of triple your horizontal resolution. So we have support for that. It has too much color fringing. You have to do some math to make it look good that we don't do yet, but it does work. So what's the next steps for Pathfinder? Want to integrate it into WebRender and Servo. WebRender is agnostic of the font rendering backend. It can use whatever it wants, so Pathfinder's a natural choice for it. We're going to have hinting of some sort. Not entirely sure how that'll work. I'm guessing right now it'll call out to the system hinter to do it because there's so much OS-specific black magic in there. But we'll have some sort of hinting because people want it. So that'll also include probably FreeType's auto hinter. We need subpixel AA to actually look good, so that'll involve some just kind of basically probably doing what FreeType does. And we'll probably have a CPU fallback of some kind because not everyone has a GPU that can do this. And the code is pretty simple to do on CPU as well. In fact, Rafe implemented it in FontRS, and that's basically all there is to it. Other nice things would be to allow generic vector rasterization. I said earlier that there was PDF, Canvas. It'd be great to use Pathfinder for that stuff too. Also emoji, which are fun. Optimizing overlapping paths, which is part of that. And bug fixes, because I have reports of it not working on people's GPUs, and sometimes it crashes on fonts or panics on some fonts you give it. And so there's going to be a decent amount of bug fixing to work out. But it's mostly there, and it's in the bug fixing phase. So benchmarks, some of you have seen this before. Pathfinder is the blue one at the bottom. I apologize that Google Docs picked confusing colors for me, but Pathfinder is the one at the bottom. The red one above it is loop blend, and lower is better. This is rasterization for a font already uploaded to the GPU, and the bottom axis is the size. So you have Pathfinder at the bottom, then loop blend, then FontRS, which is Rafe's work, then FreeType and Glyphy, which is Glyphy is a signed distance field-based rasterizer. And finally at the top, STB TrueType, which is a popular minimalist TrueType implementation used in games. And STB TrueType is interesting because it's actually essentially the same algorithm that FreeType and FontRS use in a sparse representation. But equally important is how quickly you can go from a font file on your computer to fonts on the screen. And this is kind of a measure of how much setup it takes. You can see Pathfinder is on the left, has very little setup time. Loop blend also has very little setup time. Glyphy is much worse than this chart indicates. It would be, you couldn't see the others if I actually included it, because it's building the signed distance field, which is extremely slow. FontRS, it's kind of harder to separate out setup and rasterization because it's so intertwined, but it's around there. And the parsing is essentially as fast as Pathfinder. And FreeType, again, CPU rasterizer, pretty fast setup, and slower rasterization. And SCB TrueType has much faster setup than FreeType, so it actually ends up winning there, but not by a lot. So now for the demo, and hopefully this will work. I apologize that anything GPU, anything graphics related inevitably will not show up well on AV and streams, so I apologize. But so this is a demo, and you can see you can zoom in and out, and it remains smooth. You can look at you can see the timings there, and this is easily at 60 frames per second. You can see the drawing time there is about 1 microsecond per glyph. That's the drawing the coverage. And the accumulation is at about 2/3 of a microsecond per glyph. So you can see all of it got done. In this case, the entire scene got rasterized in probably half a millisecond. So this is many hundreds of frames per second that this is running at. And you can see that it's remained smooth even if you zoom. So that's just a quick demo, and so obviously you can imagine a web page that would zoom like this. And this is on my fast GPU because that's the only one physically connected to this device, but it runs very well at 60 FPS even on the integrated GPU, which is the most important thing because we want that for power savings. So, okay. So thank you. Please try Pathfinder out. Please report bugs if it doesn't work for you. I am currently going to get to them as quickly as I can. Balancing them with feature work, don't have as much continuous integration as I'd like yet, but I'd love feedback. And all right, any questions?
Oh wait, there are people
Yes,
watching.
yes.
You want to throw me the box? Just tuck it.
Hey, How are fonts? How are emoji stored in font files, and what kind of work is going to be involved in rendering emoji?
Okay,
which
so the
we're
question-
all excited about.
Yeah.
Emoji rendering.
So the question's about emoji. So emoji are fun because there's 3 different standards for them. And Apple has one which is easy. It's just PNGs. Rafe may correct me here. I haven't looked into it too much, but Microsoft has one which is glyphs stacked on top of each other with solid colors for each one out of a color palette. So this gives you kind of flat design emoji. And that one is actually the easiest to implement, well, aside from rendering a PNG, because it's the same vector format that TrueType uses. The final one is one that I at first said incorrectly. I said that Google created it, but it was actually Mozilla, is SVGs inside fonts, which are fun because they can be animated, but nobody supports that except Firefox. But yeah, so you can put SVGs inside fonts, which is awesome. So that is the other kind of format. Probably full SVG rendering is outside of the scope of Pathfinder. You'll have to plug in an SVG renderer if you want that. But of course, that SVG renderer might in the future use Pathfinder as part of it. So any other questions? Mm-hmm. Back there.
So other than emojis, are there any corners of Unicode that might also like cause a problem with this way of font rendering and like make it not work out of the box for any particular non-Latin font?
Oh, so the question here is about whether there are problems in Unicode international text that'll make this not work. So Pathfinder actually doesn't really operate on Unicode. It operates on glyphs, which are the output of something called a shaper, which actually reads the Unicode text and determines what glyphs to use and where to put them. So most of the hard international stuff is actually not Pathfinder's responsibility. It's the responsibility of the shaper. There is a terrible shaper that I wrote, put into Pathfinder so I could get that demo working, but you shouldn't use that. You should use something production quality like HarfBuzz. And once you have that, you have glyphs. And those glyphs can be put in, and those glyphs, they're just ID numbers and locations, and you just send them on to Pathfinder. So that's mostly not Pathfinder's concern. There is some weird cases with hinting that can be necessary to make CJK glyphs work, but that's basically under the whole hinting umbrella. So mostly that stuff is out of scope of Pathfinder, and it should work for CJK and Indic and Arabic and languages that are difficult like that. Any more questions? Sure.
On the performance chart, there was a little uptick at like 100 or 108. Yeah. What's going on there?
Oh, that's because I render a whole atlas. Okay. Oh, so the question is, why is there a little uptick right around here?
Yes.
Because I render a whole atlas, and that's when it's spilled into the next line. Okay. Making the like the size basically went left to right here, and then it spilled into the next line, causing like a small increase because there was a whole nother strip with a whole bunch of empty space at the end. So that's why. Okay. Yep. That was just the specific atlas size I chose. It's just an artifact of the atlas packing algorithm.
So a while ago, there was like a Google Project Zero post about TrueType vulnerabilities, and I believe HarfBuzz has had some CVEs as well. Mm-hmm. Do you have plans to like grow out from the glyph rasterization to the shaping and parsing to reduce that surface area?
So the question is there a plan to do shaping and parsing in order to reduce security vulnerabilities? So there's actually 2 parts to that. First of all, we do the parsing ourselves of the font already. So that's basically taken care of. There isn't any unsafe code in there. The only unsafe code is to interface with GL. So that's nice. Unfortunately, hinting may make that kind of complicated because it's really hard to precisely duplicate what the system hinter does without being the system hinter. So we may have to have the hinting in the loop there somewhere. But outside of hinting, that's taken care of. There is the question of shaping, though. As far as shaping is concerned, it would be lovely to rewrite HarfBuzz in Rust. That's not anything that I have a plan to do right now. But if somebody wants to write a shaper a production quality shaper in Rust, I think that would be awesome, and you could hook that up to Pathfinder. So I'm not going to do it right now, but if somebody wants to do it, it should slot right into Pathfinder.
Do you have any kind of Rusty anecdotes from your work on Pathfinder, things where Rust provided additional benefit beyond using C or C++?
Yeah, so the question is, did Rust provide additional benefits? And one of the biggest benefits here was, the first one was memory safety, because basically I actually did a prototype of this in Objective-C because setting up a GL context is really easy in Xcode. And I tried to make the TrueType font parser secure, and after trying to think about all the possible ways I could index out of bounds, I just wrote "fix me, write this in Rust" at the top, and that really helped. It's just really hard to make sure you've dotted all your I's and crossed all your T's when it comes to parsing stuff in C and C++. It's so easy to get it wrong. That's why there have been so many vulnerabilities, and basically using Rust downgraded my mistakes from this might panic to or downgraded my mistakes from this might get you owned to this might panic, right? Which is a whole lot easier. So it just reduces the cognitive burden for me. The other nice thing is cargo. Being able to, for example, when I wanted to dump PNGs for debugging, image equals 0.2 inside cargo.toml, that was instantly done, whereas it would be more work to include download and include STB image, right, or whatever in C and C++. So definitely cargo really helps there too. Mm-hmm.
You mentioned some more advanced GPU features that were required for this approach.
Mm-hmm.
In the absence of those features, do you think that most of the approach could be salvaged on older GPUs? And if so, what would the performance expectations be?
Yes. So the question is, for advanced GPU features, could you downgrade to older GPUs? So for tessellation, so there are basically two advanced features that it makes use of, assuming you have floating point frame buffers, which are tessellation and the compute shader or image load store. And tessellation you could easily do without. You just tessellate on CPU. That means that you do have to do some CPU work when you resize, but it's not very much. My earlier version actually did all that on CPU, and the performance was just fine. So that's not so bad. I just use tessellation because it's there, and why not? But the compute shader is kind of necessary. There is a theoretical way. I've been told that there is a theoretical way that you could do it. You could do the prefix sum without using image load store, but it would require log n passes, which I kind of doubt you would beat the CPU at that point. I'd love to be proven wrong. So probably the solution for older GPUs is just going to be to run it on the CPU in that case. It's still pretty fast. Rafe has shown that. So so probably if you don't have compute shader available, then we will fall back to the CPU. The nice thing about this is that, first of all, even on CPU, this still should be faster than the other rasterizers. But also, compute shaders have been around a while, 5 years, even on integrated GPUs. So if you've bought a CPU from Intel in the past 5 years, you can run compute shader on it. So and that'll just get better over time. 5 years is already pretty far back, and a couple more years, it'll be 7 years. The computer stage will be 7 years old. So I'm not too. It is something to be concerned with, but I think that the number of people who don't have access to compute shaders is getting smaller and smaller. Anything else?
Hi. So if you have one of these Unicode horror test cases with 7 million combining characters, how much of that work is in, you can get some page and it'll just totally freeze everything. And I'm just wondering how much of that work is in the glyph rendering and how much of it is in the shaper, and where does that break down?
Okay, so the question is if you're rendering Zalgo, how much does is it in the shaper versus the font renderer? And combining characters, I believe, are actually just glyphs that get placed by the shaper. So basically, we will see that as the way we will see that in Pathfinder is a whole bunch of glyphs like right next to each other. So we'll end up basically separating them all out in the atlas and then compositing them together at the end. Remember, Pathfinder just gives you an atlas. It doesn't actually do the final compositing. So it would basically be a whole bunch of like textures, stacked on top of each other, which is something the GPU is really good at. So I wouldn't expect any particular problems with that. The shaper, on the other hand, may have a whole lot of fun parsing the GPOS table, which can run basically arbitrary regexes to position things. So the shaper's going to have some fun with that. By the time it gets to Pathfinder, it shouldn't be anything particularly hard. Anything else? Okay, well, feel free to, thank you very much, and feel free to ask me any questions afterward. And chalkboard?
Yeah, that might actually answer his question better.
Oh, like chalk duster, you mean?
Oh, chalk duster. Yes,
This may be bugged on my system right now, but I can try. Some of my kerning stuff is still kind of buggy, so. Oh, and hey.
That's the same thing as a font with a bunch of combining characters.
Yeah. Yep. This is actually kind of slow on my discrete GPU. It's a lot faster on integrated for some reason. I don't know. It may just be something strange. But yeah, this renders just fine. Okay. Thank you.
No, it's so cool.
Actually, I'm going to use the restroom before I start. Sorry. Sorry about that. Wait, I'll be fine. I got this. Cool. So, hello. On the internet, I'm without boats. I also have other names, but whatever. So, basically, the reason I'm giving this talk is that I had a blog post I wanted to write, but it wasn't the idea's not really well structured for text. So I was like, I'll just give a talk and it'll make it easier, which is not true. But yes, this is about the Orphan rules, which if you don't know what they are, if you've written any significant amount of Rust, you've probably run into them and just didn't know what it was called. And they can be pretty annoying, but this talk is basically about why, despite how frustrating you might find them, they're actually a really good idea. But there's some just general background information about Rust that I want to give before I go any further, because you'll need it to understand some of the points that I make later. So when you have something that's generic, so it takes a type parameter, that gets statically dispatched at compile time through a process called monomorphization. And so what that looks like is you'll have this this generic function that takes any type that implements toString, and then you call it on two different types, and that gets transformed in the compiled output to two different functions. So you have one function for F64 and one function for char, and then those two different calls that pass two different types to it will instead be calls to two separate functions. And this is particularly relevant for the Orphan rules in terms of how we compile libraries. So when a library exposes a concrete function, we compile that function in the library when you're compiling the library. But if it exposes a generic function, we save an intermediate representation in the metadata of your crate, and then we compile it, we monomorphize it in your binary. But so just to sort of put a point on it, this bar function, if it's in a library, it won't be compiled with the library, it'll be compiled later. But this foo function will be compiled with the library, including a monomorphization of that bar function. And why I explain this will make sense later. The other thing is about version resolution in cargo. Unlike some languages, in Rust you can have multiple versions of your dependencies in your tree. So here's just a made-up, crate dependency graph, and you'll see that the foo crate, because bar depended on 1.4, but you depended on 0.9, you have both of those versions in your tree, and that's fine. You don't get any sort of issues about namespace collision or anything. And an important detail of this is that types from 1.4 are not the same as types from 0.9, because they could have added fields to them, and then they're not the same type anymore. So the Orphan rules, to give an example, standard library has no impl of toString for any vec. So like if you have a vector of chars, that's literally just a different representation of a string, so you might think I should be able to convert it to a string, and maybe you somehow you get a vec of char in your code and you want to toString it and you can't and you're annoyed. So you implement it, and you just add this to your code and you think, good, I solved that problem. But you didn't, because you'll get into this error that only traits defined in the current crate can be implemented for arbitrary types. And that's the Orphan rules in a nutshell, that if you have an impl in your code, it's only valid if the trait is from this crate, the type is from this crate, or it's some weird edge case that I don't want to talk about right now. There's a full definition in this RFC, and it's very complicated. I've actually been told that the implementation does not completely conform to what the RFC says, so there's edge cases and everything. But this can be really frustrating as you're writing, because you wanted to add that impl, and there's a lot of cases where adding an Orphan impl could be really useful to you. Like say you found a crate on crates.io that does the thing you need, and then you use it, but you find out that it doesn't implement some trait that obviously the type should, because the author's use case was slightly different from yours, and so there's this thing where they didn't implement all the things they could have, and so you just want to implement it, but you can't. Or there's sort of this more systemic issue where when it comes to something like serialization, which is in, Serde has kind of become the standard library for that. If you have a data structure library you're using, but they didn't know about Serde and they didn't depend on Serde and add an impl, you just can't serialize that data structure, and maybe you need to, and that can be really frustrating. And so the workaround for this is that's the new type pattern, where you just create a new type that's just a wrapper around your actual type, and then you implement the trait for that new type. And this does work because you've created a new type that is now your type. This can be really annoying because you have to wrap the type and then unwrap it and call .0 to get into the inner value, and it's really frustrating. And sometimes what you actually want to wrap has a lifetime in it, and now you're dealing with explicit lifetimes, which is never any fun. And so all of this is really frustrating if you ever run into it, and it's totally reasonable to be annoyed by it. But despite that, the Orphan rules are actually very, very good. And I'm going to try to explain why. And so normally, what will happen is someone will come and post on internals.rustlang that they think that we should change this, and they don't understand, or they don't understand why, or whatever. And we kind of give this explanation that it's because of coherence. And that's actually not quite true, in the sense that, and I'm going to explain what coherence is, but Haskell has coherence, but doesn't have the Orphan rules. And we actually enforce a different property that's even stronger than coherence. So I guess, if you want to lump it under coherence, you could say that Rust is more coherent than Haskell, which is our type system is better than Haskell, which is, no, not even that. Haskell is like this ridiculously strict type system, so we're like doing something even stricter. That's kind of cool. And so coherence is about this question. So does a type T implement trait A? And if so, which input block do we dispatch methods to? And so in a coherent system, when you're like asking this question, like how do I dispatch these trait methods for this type? Wherever you are in the crate or wherever you are anywhere in general, you're going to get the same answer. So if you're compiling on Rust 1.1, 1.2, 1.3, you get the same answer for this question no matter what. It can't change between versions. And if you're in this module or that module, they'll be dispatched the same way. And that's what coherence means. And so the reason that coherence is important is what's called the hash table problem. And so in this module, so like imagine a language didn't have coherence where like Scala is an example of a language with a feature like traits, but they aren't coherent. And so in Scala, impls will start looking in the current module and then have this like rules for expanding the search out from there. And so in this module foo, you have an impl of hash for I32, and you take a hash table and you insert under the key 0 the hello string, and then you call this function from another module. And so when you're doing this insertion, you're going to be using this impl of hash. But when you go to get, so we go into this other module, this function tries to get something under the key of 0 and asserts that it's the string that you put into it. But here there's a different impl of hash. And so you have this impl A and this impl B. And as you pass the hash map between these two modules, the impl that you use changes. And so you won't have this, will you get the same value under the same, for the key 0 in the bar module as what you put in foo? Maybe, maybe not, because the way that integers are hashed will be totally different. And I think that sort of the general principle that coherence is about is this idea that methods should be dispatched based on the type that they're called on, not based on the scope that you're in. So most things are lexically scoped. Like you call a function, you're going to get a function from this namespace. But when you call a method, methods are conceptually, not in the runtime implementation, but conceptually they're passed around with the type. And so you should be getting the method for that type. And it should always be the same one. And the way that we provide coherence, or the way that Haskell does and the way that we do right now, you just have this overlapping impl rule where you can't have two impls of the same trait for the same type. So that two hash for I32 impls, you just can't compile that. The compiler will tell you, those are overlapping and they're disallowed. And this applies not only to directly the same, but they need things like this where a vector of I32 is a vector of T, so these two overlap. Or these two abstract where one's for vectors of T that implement EQ and one for vector of T2 that implement hash. And so what about a type that implements both hash and EQ? Then that would be the overlapping, right? They're not completely overlapping, but they're like a Venn diagram. And that works, but it presents this problem that every time you add an impl to your system, you need to check it against all of the other impls in your system to make sure it doesn't overlap with any of them. In order to do that check, you need to know about all the impls in your system. So that means you need to have a complete view of the universe when you're performing a coherence check. So if you have these two sibling crates that are being compiled separately from each other, they can't know that they don't have any overlaps in the other crate because they're being compiled separately. It's like a distributed systems problem. And so you have a situation like this where you have foo and bar and baz both depend on foo, and they both have an impl, a foo A for foo T, where their impl, so they both have the same exact impl that would overlap, but each of them compiles fine. And it's only when you go to depend on them that then you get a compiler error because that's not coherent. And that's essentially what Haskell does today. Though I think that they issue warnings and things. You have orphans, and they're like flags you can set where they'll just keep going even if you are incoherent, which just sounds pretty bad. So the property that we're enforcing with the orphan rules, I've made up a name for it, concordance, because it sounds like coherence. There might be, this might map to some formal logical property, and I would love to know what the name of that property is. But the idea is basically the same question again. You're trying to look up the impl for this type and trait. If you can ask that question in crate X, like if X knows about this trait and X knows about this type, no crate that X doesn't know about could possibly change the answer. So once X asks the question, the answer can't change anywhere outside of X's dependency tree. So in your crate, you ask this T impl A. When I add my crate and all of this other information to the system, that answer can't have changed. And so we know when we compile your crate that we have the final answer for that impl dispatch. And this is what the Orphan rules are actually giving us, is this knowledge that it's localized to that section of the graph. And this applies to any section of the graph, like that Baz crate knows that its types can't be changed by your crate. Foo knows that its types can't be changed by anyone else because it doesn't have any dependencies. And so that's actually like just conceptually, I think this is really cool. I don't know of any other languages that are doing this kind of like this is aware of the fact that when you're compiling, you don't have all the information. And we've inserted this limitation like in the knowledge that we're going to be separately compiling crates all over the place. And this is I think a really forward-thinking aspect of the Rust language. But it's given us a lot of really nice properties. The sort of most obvious one is what happens if we didn't have the Orphan rules when you actually have those two overlapping Orphan instances. And so you no longer can use those two crates that overlap together. And so you can imagine if Diesel and Rocket, so Rocket's like a web framework and Diesel is like ORM, if they had dependencies that had overlapping impls, you wouldn't be able to use Diesel and Rocket together. And that would be really frustrating for anyone who's trying to do web development in Rust probably. And this kind of seems a little like a far-fetched scenario, right? Because both of them have to have the same Orphan impulse. And usually you're not going to add an Orphan impulse, so even if we let you, the chance of this happening seems unlikely. But this applies when we're talking about multiple versions of the same crate. And so, like I said earlier, we allow you to have multiple versions of the same crate. If that crate has an Orphan impl, we wouldn't be allowed to let you do that. Because the way we do that is it's coherent because, so in foo 1.4, impl A for T, those are separate from foo 0.9, impl A for T, because they're different types, different traits. But if foo doesn't own either of those types and traits, if it's toString for vec, that's the same vec from the standard library and the same toString from the standard library. So those two foo dependencies are incoherent. And so essentially any library that had an Orphan impl in it, we wouldn't be able to allow you to have multiple versions of it in your dependency graph. And based on my experience compiling Rust, I pretty regularly have 2 or 3 versions of the same crate in my dependency graph. So this could be this would be a real problem that would change the way that it would violate assumptions we've made in Cargo. That would not be good. The other issue would be backwards compatibility. So if you're allowed to add an Orphan impl, if I go to add that impl where it's not an Orphan impl, like the standard library decides to add that toString impl, now anyone who has that Orphan impl can't update to the new version of Rust because their Orphan impl is conflicting with the standard library's non-Orphan impl. And so adding an impl is a breaking change if it doesn't have any new names in it. And just to show how common this is, here's that Orphan impl again. When I went to define it, I did the most obvious thing to me, which was to use the string from iter method to take treating vector as something that can be iterated over as chars, and then string can be made from an iterator of chars. And I just tested to make sure that this worked, and it didn't, because self here is a reference to a vector of chars. A reference to a vector of chars implements into iterator of references to chars. String implemented from iterator of char, but not from iterator of reference to char. But now it does. I solved this problem, but I couldn't have solved this. So I think it merged 2 days ago. So the latest nightly now has that impl. But I couldn't have added that impl if we didn't have the Orphan rules, because it would be a breaking change to add even this sort of very basic impl where it just was an oversight that it wasn't there. And so we like do this all the time, and it's dependent on the Orphan rules. And I think that both of these are like a part of this like broader principle that we're trying to maintain, where like we're going to keep updating Rust. You know, you're going to be able to keep adding things to your system, but it just works, right? Like I never worry that when I update Rust, my code is going to break, and I never worry when I add dependencies to my system that my code is going to break. And like it's just this property about Rust that is really nice, where like just the day-to-day kind of background stuff I do just always works, and the Orphan rules are like really fundamental to making that work. One thing that I think isn't obvious a lot of the time, and like I didn't come up in the discussions about specialization until I like read it in a Haskell paper. So specialization is this feature that we're working on where we allow impulse to overlap if one is more specific than the other. So for example, you could have this overlap here where you have an impl for vector of any type and an impl of vector of bytes, because bytes are more specific than any type. So we'll always use the byte one for the byte for a vector of bytes, but for anything else we'll use the vector of any type. And so as long as you can form this ordering between your impls, we can allow overlap. We're not the first people to come up with this idea. Haskell considered it, and they wrote in this paper that basically, if we use specialization, then the meaning of the program depends in detail on when context reduction takes place, and that interacts poorly with separate compilation. And to actually explain what that means, here's crate A has an impl for a vector of t, and then this function foobar, where we construct a vector of u32s, and then we use it as a vector of t. And so when this foo method is called, it dispatches to that impl in the same crate. And as I said earlier, this method, because it's not generic, or this function, because it's not generic, will be fully compiled when this crate is compiled. Then you go and you add a specialization for vectors of u32, which, if we didn't have the Orphan rules, is totally allowed. And you call foobar, like, in order for this to be coherent, foobar, that vector of u32 needs to dispatch to this impl. But this was already compiled before this impl was added. And so specialization, which is going to enable a lot of really cool patterns in Rust, and I'm very excited about, only works in the presence of the Orphan rules. Because without it, you would need to basically recompile all of your dependencies every time you compiled, because one of the impls you added could change the behavior of one of those dependencies. And so that would not be right. That would be, compile times would be terrible if we had made you do that. And so what I think is sort of the most important thing about this is that I don't think anyone during the process of designing either like cargoes allowing multiple versions or specialization really sat down and thought, oh, well, we can do this because the Orphan rules mean that we have this guarantee. Like we just sort of naturally assume that once you compile a crate, you're not going to need to re-examine it later. But the only reason we can assume that is the Orphan rules. And so to me, that seems like a really strong symbol of good design that like once, now that we have this property, we just kind of assume it, it's natural. We don't even think about it as being like a property. And it's only when, you know, you have this like, oh, they didn't add that, they didn't write all this code that I want them to write, and now I have to like work around it, that it becomes annoying. And so on that subject, I didn't write any notes for these slides. Well, like a lot of people will like have sort of, they'll think about like sort of the most obvious case, right? Like where you have two crates that don't know about each other and then they are incoherent. And they'll be like, well, what if the impulse in that crate just weren't public and they only applied to that crate? And then they don't think about how that impacts like updating your dependencies or the specialization thing. But so I think that like proposals to solve this that loosen the guarantees that we make are not viable, but there are a few ways that we can make this a little less of a pain. And so the first is automatic features. It used to be conditional dependencies, and then we changed the implementation, so the name changed. And the idea here is it's really like if I want to like add Serday serialization impulse to my crate, all of my dependencies, or everyone who depends on me now depends on Serday, and they have to compile Serday as part of their like build, even if they don't use Serday. And what people have started doing is they'll create features for their Serday and then you have to like, if you want to be able to serialize, you have to go and turn on that feature and that dependency. But what we could do is this concept of automatic features where we say, if I depend on Serday, or if one of my, like I'm a library and one of my clients depends on Serday also, I'll automatically turn on this feature. And then I will automatically start depending on Serday and have these impls. And we have an RFC for this. And this solves like some of the pain, but you still have to like, the problem with this is that you still, like that library has to write those impls. They aren't just given to, like if they just forgot to or just didn't care, like it's going to still be a pain for you. What I think is, it's a much more challenging problem, but I think is like a longer term solution is for the standard library to contain a lot of sort of high level traits. So here we have like a sequence trait in the standard library, and we allow like by better specialization and other changes to how overlapping impls work, we allow Serday to provide blanket impls for like any type of implement sequence, I will serialize this way. And then a data structure library will just say, okay, I depend on the standard library. I'm writing a sequential data structure, and so I will implement sequence. And then I depend on rope here, it's like the rope is data structure I just chose for this example, and Serday, even though they don't know about each other, ropes will implement serialize because ropes implement sequence, and anything that implements sequence also implements serialize. And so we'll get this sort of ability to chain across like crates that don't even know about each other through blanket impls. And this is through a combination of like that specialization feature and something called mutual exclusion, where we say that you can't implement both of these two traits because that would be incoherent. And then the last one, which like is an idea from Haskell called new type deriving, where you do this new type pattern, but it just automatically gets all of the methods from the type that it's wrapping. And the implementation in Haskell is unsound, so we need to figure out a different way to implement it. And I don't actually know how, but like in principle, this idea like is viable, that we could like you write a new type and then you just automatically get like charvec has len on it and stuff like that, even though you don't like have to implement it yourself. I don't know if that made any sense, but that, yeah, I'll take questions, I guess. I don't know where the, yeah.
Guess I'm first. This is not an implementation proposal, so I'm going to say that first. And it's probably going to be hard to phrase. In terms of like potentially coherent incoherence, would it be possible to like package up the impl that a particular version of a type is actually using as something like a hidden template parameter to make them actually like different types, so that when you got one, you'd have to parameterize your function on it, and then it would call the right one?
Yes. Actually, there's a pattern. Like this is, so in terms of making it hidden, like that's sort of where it gets tricky, right? Is that trying to like implicitly figure out which one to use. But like essentially you're describing implementation something where you like name the impl. And then, so if you name the impl, you import it separately and you say, okay, I want to implement this using this impl. You can effectively get that with a trick where you like add extra parameters to the trait, and then there's like, and I can show you how to do this offline. It's like kind of, you end up like implementing the trait for an associated type of another type. It's like, it's tricky, but it works, and it's totally coherent. But I wouldn't want to program with it. Like an impl doesn't conceptually have a name, right? Like you don't like think about like the implement of toString for vec of char. Like that isn't a thing. And I wouldn't want to have to like, for every impl that I'm going to be using, have to like name it and pick it as I'm like going through. And that's where like implicits come in, right? Where you can like kind of, it figures it out for you, but there's ultimately implicits to certain like Scala aren't coherent. So I don't know how we could do that coherently.
Hi, so you mentioned whether there are other languages that implement similar restrictions. And there's actually a very close analog of this problem in the literature on type checking multi-methods, which is dynamic dispatch. And so there's some nice papers by Todd Milstein and Craig Chambers from the early 2000s, the University of Washington, on basically implementing restrictions that are very, very closely analogous to the Orphan rule. Namely that you can extend a multi-method in either the package where the multi-method is declared or in the package where the type of what's called the distinguished argument position is declared. And so those would be interesting papers for you to look at.
Thank you.
Hi, I have experience with Haskell, so I just had some questions about that. Is one you said Haskell doesn't have Orphan rules? Did I hear that right?
Yeah, my understanding is that Haskell has a warning, but it
Right.
doesn't fail to compile if you have an Orphan instance.
Yeah, so I mean, it's basically commonplace in Haskell just to compile such that a warning's a failure. So it basically does have Orphan rules that are adhered to, and Haskell
Right.
basically has all these problems that it's roughly about the same situation.
You would
Yeah.
typically turn the warning off, but like you know that you're doing something iffy when you implement it. So you have an annotation.
So I think if you ever published a library with an Orphan instance, you would get a lot of flack for that, and no one would use your library. This comes back to one of the features of Haskell is you can turn it off, and that's very useful for the application author who's not publishing a crate for other people, but this is my code. I'm not sharing it with anybody else, and I don't want to do the new type dance, and
Yeah.
I want to just define my implementation. That's one thing that's easy to do in Haskell, which can be abused, but it would be a nice feature to have for power users that know
Yeah.
what they're doing, etc.
I have two thoughts about that.
Yeah.
The first is Edward Met, I don't know how to pronounce his last name because there's a
Yeah.
KM in it. I don't know how to, I'm sorry. Gave a talk about coherence, basically arguing why, like, the thing that Haskell and Rust share is better than like what Scala has where you aren't coherent.
Mm-hmm.
In which he talked about how in Scala, people have there's a community standard not to be incoherent. And you just kind of have this convention, which is essentially what Haskell has around this property about orphans. And so I think there's an analogy between saying, coherence is better than just like an agreement between people. And similarly, concordance or whatever is better than an agreement between people because you just always have it. And you're right that in a binary, you could just not want to deal with it and get around it. But then in that binary, you're still going to have the issues around specialization won't work properly. If you override have an orphan that would specialize something, and then when you go to update the standard library, you might not be able to update. And so I still worry about letting people turn it off even in binaries because of these other properties that don't only affect libraries, basically.
Yeah, I mean, I think it's something that you have to opt into, and I'm opting into this, so I'm going to run into these problems. Yeah, I think the automatic feature turning on is a great idea because the end result of this problem that you're talking about is that you have this great mechanism for extensibility, but you can't it actually ruins the way you have to write your code. You have to put this here, you have to put this here. This package has to depend on this to pull in these, and it has all these horrible effects for modularity. So anything you can figure out like that to help out with it is great. And then I was also just wondering why do you say the Haskell new type driving is unsound?
There's some sort of unsoundness involving associated types and not because the way it's implemented through the type system. I think if we implemented it, would be through essentially a macro, and so it would generate things that would get type checked, and so we wouldn't have that kind of issue. But just the way it's implemented in Haskell.
Yeah,
has
I mean, in
some
Haskell
unsoundness.
you can do things like violate invariance because because something has the wrong. You redefine what the ordering is on things, and so if you have sort of a container that contains ordered things, and then you have the exact same representation of that, but you use new type to give it a different ordering, then suddenly you've violated invariance of that container. So you have to worry about things like that. Like if it were in a red-black tree or something. you convert integers to negated integers or something. I mean, I would say maybe this is as much a comment as a question, but I feel like I believe your conclusion and not necessarily your reasoning, because it's just the orphan instances aren't really a problem in Haskell in practice. On the other hand, if you say like, hey, I'm going to give you specialization, then I'd say, well, it's totally worth it to give up orphan instances, even though, you know, when I do use orphan instances in Haskell, it's a great escape hatch to have.
Yeah, I think specialization is the like sort of strongest argument.
If you started with that would be even happier.
Something that we honestly didn't realize, I think, as we were implementing specialization, that we were relying on this
and
property.
just one other thing that this is probably never going to happen, but I did once put up a pre-RFC for something called forward impulse, where you declare that an impl exists in a place where you can't define it, and then when you actually implement that, you sort of import the declaration of that impl and mention it, and this lets you step around a lot of the orphan rules. And the precise use case was that I'm an application like Servo with 20 crates inside that we're not publishing, and we want to be able to do some shenanigans. So it's there, but it's sort of like, I think the solutions like automatic features and many other things, they're the better directions to go in to fix this problem. However, it's there on internals if you're interested in looking at it. So yeah.
I think Aaron actually likes that idea, so that might.
Ooh, okay.
I don't like it, but.
Yes, but Aaron
Yeah,
I can.
Yeah.
I can work with that.
Yeah.
But the thing is, I don't like the idea much either. It's just been there, and I've just wrote it down. So
Yeah.
Yeah. Shit.
There are napkins around here. Yeah. Yeah. Anyway, so as an ordinary user of Rust who might like to implement not my trait on not my type, I kind of really like this new type deriving solution to the problem. And so I'm wondering if you go into a little bit more detail about exactly why that's unsound.
Oh, I honestly don't fully understand why it's unsound in Haskell, but it wouldn't be unsound if we implemented it in Rust, we would definitely implement it in a way where this is just code generation and then I'll get type checked, and so it wouldn't be unsound. I don't have a detailed proposal for it though. Like it's hard to say like this here, just new type deriving, like what traits do you get from this declaration, right? Like definitely you shouldn't get toString because you've implemented toString, but how do we know that and things like that? And also there are some implements that just won't work, like associated types can become an issue because maybe the associated type is self and like it'll be different here where it's, and so there are like a couple of issues around that, I think. But I think this is a viable approach that just hasn't been explored fully.
I want to put in a plug for the automatic feature thing that I was thinking we have a use case, and I want to kind of speak to like the community ecosystem aspect of that. So we want to depend on Cairo, and Cairo has a dependency on glib because they want the from glib pointer to glib pointer traits, but we don't want to depend on glib. So the thing that's great about the automatic feature thing is that we can send a PR to say glib is an automatic feature. So that won't break. We were thinking of sending a PR and we're like, oh, we got to update all of the things that depend on it so that they actually plumb those features through the configuration. And so like that's a use case where we actually want to subtract. And I think it's like a great freedom that you can add and subtract completely at will just by patching that repo without causing like a greater disruption.
Yes, though I think that it's a minor breaking change possibly if they're re-exporting from that, because then people are using it without explicitly depending on. I thought it was pronounced glib, but yeah.
It might be a minor breaking change, but it sounds like it would
But
be
yeah,
a
but they
lot
just have to
less
add
breaking.
the dependency.
Yeah.
Yeah.
I was wondering if there's been any consideration of the idea of basically declaring a dependency on a crate such that your version of that crate that you depend on is considered unique to your crate, which would effectively be like a new type on the scale of an entire crate, which then, because you're guaranteed that sort of by definition no other crate has a dependency that's considered the same as your dependency, you'd then be able to declare impls on it arbitrarily because there'd be no other dependencies on it. You'd effectively own the code.
That hasn't been considered. Only thing about that is that because of the specialization issue, you would have to recompile that crate every time your crate compiles. It would essentially be like saying that crate is just a module in your system, and then it gets compiled together every time. That actually, like if you're willing to pay that compilation cost, that sounds like a possibly reasonable approach. Yeah, maybe.
One more question.
What is actually blocking specialization from being stable right now?
Some questions about specializing on lifetimes, and chalk, an implementation issue. The current trait system is kind of a mess, and Nico is writing a new implementation of it based on Prolog, which once that's ready and replaces the existing implementation, then it's basically we can reason about it much more easily because we can just test things very quickly, and so it's almost ready basically.
Okay. I also read from Nico's blog that struct and enum inheritance was blocked on, or they're trying to look at how specialization is going first before they kind of dive into struct and enum inheritance. Is that still true?
Yeah, so specialization covers a lot of the use cases for inheritance, and also a lot of what we essentially want to build inheritance piecemeal through things like specialization and things like that. Thank you.
Yeah, I know.
Something mini.
Yeah.
I don't have any of those guys. I think I might do.
Oh yeah. Yeah. I'm surprised there's no camera here. There is something up upstairs. I don't know what it does.
All right, take it away.
Awesome. All right. Hey, I'm Sergio. We're talking about Rocket, the web framework, not the physical item. But I can also talk about the physical item if you want. So Rocket is a web framework for Rust that ideally makes it simple to write very fast web applications without sacrificing flexibility, as in you should be able to do what you actually want to do, not what the web framework makes you do, or type safety, as in you shouldn't have to unwrap or use dynamic typing to get your things in the type that you want them to be. So before I talk about how Rocket works, just want to give you a brief synopsis of the history of Rocket. So here's the history of Rocket in 3 points. So Rocket launched a couple of months ago, December 23rd, 2016. It we got version 0.2 out about a month and a half after that. And well, now we're here. Now we're the third dot. So, short history. But it's made a lot of impact, I think. I mean, it's hard to say, really. I don't know. People just kind of use it. They don't say that they use it. But I do know that at least 5 to 10 to 20 companies are using it in production, which astonishes me. It's mind-blowing like why is, hopefully it's behind Nginx or something. That's my recommendation. People on GitHub seem to like it. It's got over 1,700 stars and growing by 10, 20 each day or so. The one really cool thing, the thing that really, really excites me, the thing that makes me really, really happy, is that I see a lot of people using Rust because of Rocket. I've had a bunch of people who had never written any Rust before, and they started writing Rust because of Rocket. So that makes me really, really excited. It also means I get some very interesting PRs that say, this is the first Rust code I've ever written. Hopefully it's okay. So that's kind of fun. Before that, I had worked on Rocket for about 8 months before I launched it. So, definitely had some 8 months of full-time work, which is like, how do you do that? I don't know. So it's had some thought put into it, but I'm always open to thoughts that you might have. Our GitHub is very, very active with people, opining and telling me what they think, which is fun. It's a lot of fun. So if you have opinions about what you might see here, or you already know about it, please feel free to post on GitHub or also on every web chat thing, Matrix and IRC. Okay, so here's Hello World. It's really, really simple. Hopefully. It's a function. We're calling it world. And it returns a string. And that's all the function does. And then you sort of tell Rocket what requests are going to match this function. We're going to call this function a handler, and we're going to call the thing above it a route annotation of some sort. And that's Hello World. It really is 4 lines, plus you got to import things, and you need a main function to actually run this thing. But so the main component of Rocket is these routes and these handlers. So a route is composed of 2 things. One is the set of matching parameters, and that's this thing up here that says, okay, a request is coming in from the outside world. When should we run this function? What things have to be true about that request for this function to run? In this case, the request has to be a GET request, an HTTP GET request to the path/world. And if that's true, then Rocket will run your function. And the second part, of course, is what do we do when this thing matches? In this case, we just return the hello world string. And so if you were to actually run this code and you visited /world, you would in fact see the string hello world in your browser. And if you don't believe me, there's you can do it yourself. It happens. So that's the general idea behind Rocket. You have these decorators. You decorate your handlers. You tell Rocket about your route, and then Rocket dispatches requests to your routes. To tell Rocket about your route, you have to do something called mounting. If you're familiar with other web frameworks that have mounting, then you know mounting, obviously. Mounting essentially means you're going to namespace a bunch of routes. So in this case, we're mounting to the /hello path. And so any routes that you mount to that path will have that path prepended. So in this case, to actually get to the world route, you have to go to /hello/world. And you can pass in as many routes as you want. And there's another macro there. Macros everywhere. We're very proud about our macros. Okay. And then finally, to actually get your thing serving requests, you have to launch the Rocket. Otherwise, the Rocket is just kind of sitting on the launch pad. So you got to launch the thing. And when you launch Rocket, your Rocket application, you start the server, and it just kind of goes. It's very fast, does its thing, and it gives you nice. That's the launch method there. It gives you nice little output. Tells you what's going on in the world. Tells you about the world that you've configured, and then it says that it's launched. And then it also prints emojis. Some people really dislike the emojis. I'm really surprised. You might be one of those people. There's no way to turn them off either. That's my favorite part. There's no way. It's awesome. It's just fantastic. Yeah, there's a PR about that. Yeah. All right, so that's cool and all, but that's not particularly interesting. Great, we can mark our routes up and we can dispatch requests to them. What else can we do? Well, you might want to actually get some data from the user. One way you might do that is through the path. You might say some segment in our path is dynamic, and we want to then take this dynamic segment and transform it into some type that we want. And so this is how you would do that. So here's another handler. We'll call this one hello. It's a handler that runs when it matches against GET requests to this path here. This path has two dynamic segments. The first one we're calling name, the second one we're calling age. So these dynamic segments, these parameters, you put them in brackets and they match any text in that segment. So, if we had /Sergio /5000 or whatever, that would match. Actually, in this case, it wouldn't, but we'll get to that. And then you have to specify the type of this dynamic parameter. Because the web is a string and Rust is not a string, so we have to somehow tell Rocket how to convert the web into Rust. And in this case, we just use the types in the signature. And so you can use any type that you want, as long as that type implements from param. And Rocket implements from param for pretty much any type that you'd like it to. Some people want to implement it for more types in the standard library, and then we have coherence issues. So, problems. But, GitHub. And the cool thing, this is where Rocket gets pretty interesting, is that your handler only runs if Rocket is able to actually parse that string into the type that you asked for. Otherwise, we couldn't even call this function. It's just the type system won't let us call this function if we don't have the thing of the right type. And the way we do that is we call the implementation of from param for that type. And so as you might imagine, for string, it does nothing because the web is already a string, so we don't have to do anything. It's just the identity. For age, we parse the integer into, in this case, an I8. And so anything within -256 to 255 will parse. Anything outside of that will not parse. Or -128 to 127, my bad, 1 bit. So what happens when they don't actually parse? What happens when you don't have the right type? Well, something that's a little different, nothing else that I know actually does this. The request gets into this goes through this forwarded mechanism. And we'll see what this really means when I explain what forwarding is, but for now, just understand that it means that it doesn't call your handler. The goal here is for your handler to only get called if all of the entire world from the request is created can be validated. That is the core premise of Rocket. Your handler will only ever run if the world is what you expect it to be. Okay, so that's dynamic paths. One really cool thing that we get is if you mess up, then we give you really nice errors. So in this case, say you declared age in your route attribute, but you did not actually have it be a function parameter. So Rocket, if we didn't have this error, it would just fail to compile, and then you'd be very confused. But thankfully we can plug into Rocket to Rust, the Rust compiler, and give you nice errors with colors. But no emojis. That's Rocket version 1. Okay, so let's talk about that forwarding thing I talked about. So here we have two routes. We have user and user stir. So the user route matches against an ID as a dynamic segment, but so does user stir. The difference is the type of ID. In the first one, we have a usize. In the second one, we have a string. And you see this rack equals 2 thing. So as I said before, when you can't derive the type from the string, then derivation fails. And what happens is the request gets forwarded. And what forwarding means is that Rocket is going to try to find the next thing that matches that HTTP request, where the route attribute matches. We call that a collision, but just think of it as a match. And it will try things in order, in rank order. So every route gets a rank of 0 or 1 by default. 0 if it's a static path, i.e. you have no dynamic segments, and 1 if you have dynamic segments. That's just because that's what made sense to me. Thankfully, no one has complained about that one yet. And then once you try the first one and derivation fails, it gets forwarded to the next one, and so on and so forth until there's nothing left, and then Rocket will give you a 404, or not you, but your client. And so in this case, if we had a request to user / Michael, for example, the first Rocket would try that route on the top. That route would fail because we can't parse Michael into usize, so Rocket would then try the next rank type route, in this case being the one at the bottom. Anything parses a string, so that one will always pass. By the way, feel free to ask any questions if something is not clear. Okay, So that's forwarding and ranking. All right, now this is the other cool thing. So Rocket has this concept of request guards, which again is not something that I've seen elsewhere, but turns out it solves a lot of interesting issues in a hopefully a nice way. So request guards are types that implement the from request trait. And you can have as many of these things as you want in your handler, an arbitrary number of from request parameters. They don't appear in the route attributes, they only appear in the function signature, in your handler signature. Anything that appears in a handler signature that is not in the route attributes is implicitly a request guard. And so you'll get a compile time error if you add some type that it doesn't actually implement from request and is also not in your attribute list. And what happens here is that Rocket will call the from request implementation in the order that you write them in for each of those types. And your handler will only get called if all of those from request implementations succeed. And so here we have an example where we have some admin panel route. And well, you don't want non-admin users to be able to access this route. So you want to check that if someone accesses this route, they in fact are an admin user. So we have this admin user type that is a request guard. And then Rocket will call the from request implementation, which we might imagine checks the cookies for some session, looks up the user, checks that it's in fact an admin, and only then does it return success. Now, when we combine request guards with forwarding, we get really cool stuff. So request guards can succeed, fail, or forward. You can choose to do one of the three. And so here we have more admin panel routes. We have the one we just saw at the very top. In the middle, we have a rank 2 admin panel, and at the bottom, we have a rank 3. Now, the rank 2 one has a request guard as well, but it's a user request guard, not an admin user. So that one should pass if there's just a regular user logged in. And the third one has no request guards. So it'll always match as long as the path is correct. And so what we've done here is actually encode policy. So when someone hits our admin panel route, or sorry, our /admin path, then first we check if it's an admin user, and then we run that first route. And then we check if it's a regular user, and we run that second route. And then, well, we don't check anything, we just run that third route. You want to imagine the first thing, in the first case, we actually present the admin panel. In the second case, we say, sorry, this is only for admin users. You're not an admin user, Michael, Bob, whoever you are. In the third case, we say, you're not even logged in. Please log in. You may or may not be an admin user. So this is really, really different than what you would do in pretty much anything else. You'd probably do this with some kind of if condition, and then sort of proceed that way. And again, the guarantee that Rocket's giving you is that your thing just won't get called if the request guards aren't maintained. So you have no worry that your first thing will get called if there isn't an admin user. Okay. So something that was added in version 0.2 that's made a lot of people's lives very happy is managed state. And this is really sort of a use of request guards. So managed state is a request guard. So one thing you might want to do is have a hit counter on your website. I don't know why you would, but maybe you'd want to do that. And so you have to maintain this state somewhere. We write Rust, so we're not privy about global state, so we need to do something else. And what you can do is you can ask Rocket to manage that state for you, and then ask Rocket for the state back. So what you do is you declare some structure. Here we're going to call it hit count, and it has to be, if you want to modify it, it has to be send and sync. So it has to be thread safe and sendable across threads. So if we actually want to modify this hit count, we're going to use an atomic unsigned integer. And then you call manage on the Rocket instance. So you ignite the Rocket, and then you call manage, and you pass in the state that you want Rocket to manage. And then when you're ready, you just add a state request guard. And if the state exists, then Rocket will give you the state, and you can do whatever you want. And if it doesn't, then that route won't pass. There's a lint that will tell you when you try to access state that is not actually managed. So in practice, it should never happen that a state guard is not passed. So the state type is managed by Rocket, and then you retrieve it by a request guard. And so in our index route, we get that state. We fetch the internal usize, atomic usize. We do a fetch add, which just means we're going to add. And so now we've incremented our hit count. Now, we sort of talked about parsing a little bit of data and the stuff in the dynamic segments, but there's more data to parse. Body data. So you might have a form. Well, we have this data attribute. This data equals less than task, more than. So you know task is an attribute, a parameter. And so that's why it appears in our function signature new. And then we have this type form. So I'm going to call these things data guards. So we have request guards, then we have data guards. So as the word guard might imply, you have to implement a trait. In this case, it's from data. So anything that implements from data can be the type of anything that is a target, i.e. the parameter of this data equals attribute. And then Rocket will do what you probably expect. It'll call this from data thing that parses the body, validates the body data is what you expect it to be, in this case an HTTP form, and then pass it into your structure. And if that parsing fails, then you don't get called. Now this is, you wrote nothing additional to get this. You just wrote that you want a form, that the form is in the data, and everything else happened for you. This is literally what you write. You write nothing else. Oh, you need to tell us what this task is. But we use serialization, deserialization to automatically serialize and deserialize the form from your structure. And the way we do that is with this from form trait. So form itself takes in a generic parameter, which must implement from form. From form is derivable, so in order to get your structure to be a form, you just do derive from form. And everything else happens for you. There's other cool things here, but I'll let you read about that later. We can also do the same thing for JSON. So we just change form to JSON, and this time we implement deserialize, and everything else happens for you. You also have this format attribute, which says this thing should only match things that have application/JSON in their content type. In this case, it's redundant because the JSON type itself checks that the content type is JSON. But in this case, it just shows intent. This thing is meant to work only for JSON data. Okay. So finally, we've done a bunch of stuff to validate a request. We actually want to give something back to the user. So far, we've seen strings. Strings are fun, but not super fun. So let's do something even funner. Well, this is still a string. But it doesn't have to be a string. It can be anything. It can be any type that implements responder, which is another trait. You can implement it for your own types. Maybe you have some custom serialization thing, you want to implement it, you can do it yourself. Rocket has a bunch of built-in responders, including JSON, templates, redirects, status codes, just, whatever you want. It's probably in there. Flash messages, other things. And they can also fail because, for example, if we're going to serialize some structure into some arbitrary format and the structure is not amenable to that format, then it's going to fail. And what happens then is that the responder can decide to take the error and forward it to something called a catcher, which I'm not going to talk about, but a catcher is an error handler, essentially. Okay, so I'm going to say endless possibilities because I don't know what you can do, but these are 4 and then 1 that says I don't know what you can do. So one cool thing you can do with Rocket is you can mount some third-party code. Someone else could implement some routes, like OAuth, and then you can just mount it, bring it into your namespace, and now you have routes in your application that you didn't write. And it just happens for free. And they can also get your managed state if you let them, which is kind of neat. As we saw, you can encode and centralize policy with request guards. I think this is an underexplored area. One thing I really want to happen is for me or someone to write a user authentication system, which I think would be really, really cool in Rocket. I don't know how to do it. I don't know. Someone should do it. At some point I'll get to it if no one does it. It makes parsing data just super simple. There's no middleware. You just tell Rocket you want some JSON, and it just does it for you. And if it doesn't do it for you, you can do it yourself. And the really important thing is that when you look at a handler, when you look at a handler's code, you know what must be true about the world for that code to run. All you have to do is look at the signature, look at the attribute, and you know everything that must be true and all the things that must be true for this request to run. Which for me is just really nice. I mean, it's really, really nice. If you look at someone else's code, for example, written in Rocket, it's always obvious what must be true because it's there for something to run. And it's always obvious when that thing will run. And like I said, there's a bunch of other things I'm sure I haven't thought about. If you think about them, please let me know. And there's a bunch more stuff that Rocket lets you do. There's templates, as I said. Obviously, you can mess with cookies. Everything is streamed. Nothing is stored in memory beyond a few kilobytes. There are configuration environments, development, staging, production. Everything is configurable by environment variables or a config file. You can also parse query parameters. Looks kind of the same as parsing forms. There's built-in testing. You don't have to reach outside of anything to test. It goes through the entire request mechanism without spinning up server. So, it does most of the things you'd want it to do. So that's Rocket. It's in progress. We're at version 0.2.2. There's like a lot of more versions to go before we get to version 1. There are very good reasons for it not to be version 1. But I'm pretty happy with it. You guys should try it out. There's a website. You can go there with your web browser, and there's stuff there. There's a guide. There's a tutorial. There are a bunch of documentation, news. You can get to the GitHub page from there. There's a lot of docs. The guide is pretty big. And then we're also on ircmozilla.org at #Rocket, and we're on Matrix as a bridge channel if you know or care what Matrix is. All right, that's Rocket. Thanks. Let me just show you rocket.rs, just so it's not scary next time. That's not rocket.rs. Yeah, Chrome is bad. All right, here's Rocket. You go here. There's some buttons. You might click on those buttons. One of those takes us to a guide, and you can, follow it and write Rocket.
All right. Hey, Sergio. Thanks. This is great. I played around with Rocket for the underhanded Rust example thing. There's a little thing with Rocket and Iron. Cool. It was a lot of fun. I was wondering when are we going to get you off of nightly Rust?
Let's find out. All right.
Yeah, those are going to be stabilized like in a month or so.
Yeah.
Okay.
So I think we need most of those, but not all of those. If there's like something that the Rust community can't figure out, and everything else is done, I'd be happy to work around it to get it working on unstable. That'd be awesome.
So you described what happens, how things match and what happens if there's a match error and how you can use ranks to disambiguate that. But what happens when you have sort of a multi-match, right? If you have your age example, if I have an age with an I8 and an age with a U8,
yep,
those can both match 6.
Yep.
How do you?
Yeah, so we call that a collision, okay. And Rocket will scream at you when it starts. Yeah, it will say, all of these things collide, fix it, we're going to give you an arbitrary match. Yeah, I think it should be an error. Right now it's a warning. It would be awesome if we could detect it at compile time. It's just impossible, unfortunately.
So I have 2 questions. The annotations remind me a lot of Drop Wizard, which has like metrics and logging and things like that are very pluggable. Is that supported currently in Rocket, or do you have plans to? Like middleware?
Yeah, so there's no middleware. I think middleware is generally evil. And so there will never be middleware that you're like super familiar with. I think because a lot of things that you do in middleware, for example, if you use Iron, one thing you do with middleware is take a body and parse it, put it in a type map, and then get it out later on. We don't have to do that. We have stronger features. So we won't see middleware in the sense that you might be used to. For exactly the things that you said, things like logging and metrics, they have an interesting property, which is they don't have to pass any information to the next thing. At worst, they have to pass information from the beginning to the end. And so I'm calling them fairings for now, because the fairings cover the Rocket. And so I think there's an open issue about this. I've sort of laid out my opinions. People have told me I'm wrong. Yeah, so that's yeah. At some point, yes, I definitely think Rocket should be able to handle that. If you want to do it now, you can do it with request cards, for example, and custom responders. It's not fun. So no, you can't do it yet, but you definitely will be able to do it soon. Cool. It's a priority.
And then question number 2, So is this using Hyper under the hood?
This is using Hyper under the hood.
And when Hyper's Tokyo branch lands and is released, what are your plans for Rocket? Like, can I return a future from a handler?
There's also an open issue for this. So I don't want to commit to any kind of design because I don't know what the right thing is yet. I haven't thought about it enough. What I do want to say is Rocket will certainly be async. Async is the right thing to do. Whether we'll use Hyper or not is a question. Whether we'll use futures or not is a question. It depends how it works out. You know, it's still pretty early. Tokyo's great, but it's very early. I mean, if everyone's using futures, then there's no reason Rocket should not use futures. That's just going to create, you know, a bad environment. So I just want to see what happens with the async world in Rust, and we'll do what the right thing is, which I don't know what it is yet.
Okay, I'm a bad throw.
So you mentioned you have state. Is state a good place to put your database connection? Is that what it's designed for, or where should I put my database connection?
Yeah, so that's what. So for example, we have to do example, and that's what the to do example does. In fact, it puts a pull into manage state, and then you get the pull. Actually, we implement from request for a single connection. The from request thing is another request guard that gets the pull and actually gives you one connection. So instead of asking for a pull and then getting a connection, you just get a connection. So that's what I would recommend now. And you can see that was totally confusing, which it probably was. Look at the to-do example, that's what it does. But rather, there's an open issue. I definitely want to have database support in Rocket contrib, which is the accompanying crate, which will give you one connection, and you can configure it in the config.toml file. But for now, yeah, manage state.
Hi. Let's see. First, I wanted to definitely second the desire for stable Rust, but I'm curious, like, how much you envision the API changing before it gets to 1.0. Like, do you think it's pretty similar to what it is now, or is it going to be looking drastically differently?
I think it'll be very, very similar to what it is now. There's been no like, wow, that was a bad decision. We need to fix that. I don't see that happening. It went through a lot of changes before it was released. I didn't want to release if it was going to go through a lot of changes. For example, like 3 months before I released, everything was in memory. Nothing was streaming. It was a huge change to make everything streaming. So I think all of those major things have been changed already. I don't think we'll see any major changes by 1.0. I don't think async, for example, async might be a thing that completely changes everything, but I don't think so. For example, we could just return a feature, and then everything just kind of works as you'd want it to. So no, I don't think things will change significantly by version 1. I think things will look pretty much the same. I think most of the applications you do right now will work in version 1 as well.
So what happens if I try to mock up my own state storage by defining a struct, making a bunch of defining an impl with a bunch of methods with a at mute or and mute self on them, and then try to put the get and post annotations on those methods?
If you can put annotations on methods, is that the question?
Yeah.
Okay, you'll get it. Rocket will say, no, sorry, you can only annotate functions. That's what will happen. But there's also an open issue about resources, which would let you implement a resource trait for a structure, annotate that structure, and then Rocket will create a bunch of routes for you, get, put, post, delete, that do CRUD, essentially. No one seems to agree or disagree whether that's a good thing or bad thing, but it's an open issue. So if you have opinions on that, feel free to comment. All right, anything else? Cool, thank you.
Yeah. Thanks for coming. You can still stick around for a while until we get kicked out. And yeah. And I hope you come next time.